Welcome to the deep dive. Today we're doing something a bit different, really focusing laser-like on just one huge piece of research.
Yeah.
It's a study that tries to map out, well, one of the biggest energy transitions happening anywhere. We are digging deep into the role that battery and water storage play in Saudi Arabia's transition to an integrated 100% renewable energy power system. Quite a title.
It really tells you the scale, doesn't it? And our mission here, for you listening, is to get under the hood of the logistics. I mean, think about it. Saudi Arabia, a country historically synonymous with fossil fuels, but also facing immense water challenges, relying heavily on desalination. So this study asks, how can they actually hit net zero by mid-century? Practically, cost-effectively, and critically, by linking up power, water, and industrial gas production.
Right, and the core issue, the tension we're going to unpack, is storage. It always comes back to storage with renewables. When you're talking 100% solar, mostly you need somewhere to put that energy for the night. And here, Saudi Arabia has these two big options. Batteries, the chemical route.
The fast, scalable option.
Or using their massive desalination and water systems as a kind of physical storage, storing actual water. So which one really provides the flexibility they need at the right price? That's the question. Okay, let's set the scene first. Why this massive shift? We know climate change is a driver globally, but for Saudi Arabia, it's almost existential, isn't it? Particularly the water situation.
Absolutely. The study highlights this right away. Their water scarcity is it's staggering. We're talking only about 85 cubic meters of renewable water per person per year.
85, compared to what globally?
Well, the global average is more like 6,000 cubic meters. So yeah, it's extreme. They simply can't keep powering essential desalination using expensive, polluting fossil fuels. It's not sustainable. So Vision 2030, the Paris Agreement, these aren't just, nice to haves. They're survival plans.
Okay, so the need is clear. Given that, what's the pathway this study found? Does a 100% renewable system, does it actually work out on paper? Financially.
It does, and maybe faster than you'd think. The least cost model suggests Saudi Arabia can get to a fully 100% renewable system by 2040.
By 2040.
Yeah. And here's the real kicker. It actually saves them a huge amount of money over time.
Okay, let's talk costs then. The levelized cost of electricity, the LCOE, that's the all-in cost, building and running the power plants.
Right. And that LCOE is projected to absolutely plummet. The study puts the 2015 figure at nearly $140 per megawatt hour.
Okay, pretty high.
Very. But by 2050, under this renewable system, it crashes down to about $41.5 per megawatt hour.
$41. That's a massive drop.
It really is. And that economic shift is powerful evidence. It shows that the transition isn't just about the environment, it's becoming the smart economic choice too.
So the economics work. But what technologies are actually doing the heavy lifting to get that cost so low?
The study is very clear on this. Two things dominate. Solar PV, specifically the single-axis tracking kind that follows the sun.
Right, maximizing the capture.
Exactly. And battery storage, those are the cornerstones. By 2050, the projections show that solar PV provides something like 79% of all electricity generated. 79%.
Incredible. And the batteries.
Batteries step up massively. Their output covers about 30% of the total electricity demand by 2050. They're the main buffer, smoothing things out.
Which brings us right back to that core idea, flexibility. If you're 79% solar, you absolutely need ways to handle nights, cloudy days. The system needs to adapt constantly. Batteries are obvious.
Obvious, yes. But Saudi Arabia has this unique twist with its huge water sector. Desalination, specifically seawater reverse osmosis, or SWRO, uses a ton of electricity.
Okay.
So the thinking is, if you already need these power-hungry plants and you need water storage anyway, maybe you can combine them. Use the water system itself as a sort of giant flexible load, maybe even a battery.
That's a clever concept. Got excess solar, crank up the desalination, make extra fresh water, and just store the water. You're storing potential energy, effectively. Does integrating them like that actually save money in the model?
It does, yeah. The study put a number on it. Integrating power and desalination cut the total annual system cost by somewhere between 1% and 6% compared to operating them completely separately.
Okay, so 1 to 6% is something. Definitely an optimization gain.
It is. But here's where it gets, complicated. When the model optimizes for the absolute lowest cost, how does it decide to run those desalination plants? Flexibly, turning them on and off with cheap power. Or
what did it find?
It found the opposite. The least cost approach runs those expensive SWRO plants almost constantly. We're talking baseload operation. By 2050, the calculated full load hours are around 8,733 hours a year.
Hold on, 8,733 hours out of 8,760 in a year. That's running basically nonstop, like 99.7% of the time.
Precisely. Constant baseload operation. And the water storage tanks. They end up only covering demand for the leftover 27 hours or so in the entire year.
Wow, so the system chooses cheap water over grid flexibility.
That seems to be the economic logic. The capital cost of these huge SWRO plants is so high, the cheapest way to produce water is to run them flat out all the time to spread that investment cost over the maximum possible output.
So the water storage becomes just a tiny emergency backup, not really a flexibility tool for the grid?
That's what the baseline model suggests. Even though technically possible, the economics of the desalination plant itself dictate constant operation.
Okay, that's a really key finding. You build this massive, specialized thing, you're kind of forced to run it constantly to make the numbers work. It limits its potential use for other things, like grid flexibility.
Exactly. And that realization sets up this fascinating comparison, this economic stress test. If the high cost of SWRO prevents water storage from being flexible, what happens if we artificially change the costs? If storage tech gets cheaper?
Ah, the sensitivity analysis. This is where you tweak the inputs and see how the system reacts.
Yeah.
Which storage type batteries or water really wins the flexibility race if costs fall?
Okay.
Well, let's look at scenario A, cheaper desalination plants. What if building those big SWRO units got significantly cheaper? Does water storage finally become a contender for flexibility?
You'd think so, logically, but the model showed surprising resistance. They had to slash the SWRO capital cost by a huge 50%. The authors called this level of reduction unrealistic just to see any significant system cost reduction.
And how much reduction did that unrealistic 50% cut achieve?
Only a maximum of about 2.13% in the total annual system cost by 2050. Very small impact, relatively speaking.
And did it change how the plants operate? Do they run less?
Barely. Even with costs halved, the SWRO plant's running time only dropped by about 1% in 2050. The system still preferred running them baseload.
Okay, that strongly suggests water production economics are just fundamentally geared towards constant operation. Flexibility isn't its main game, even if it gets cheaper.
It seems so. Now contrast that with scenario B, decreasing battery capex. This scenario is much closer to reality because we know battery costs are falling fast. What happens when the model sees cheaper batteries?
Right, this is the interesting one.
And the results are dramatic. Just a 20% reduction in battery construction costs completely reshaped the modeled system, almost immediately.
How so?
Battery storage output just exploded. It increased by 80% in the 2030 timeframe alone. Cheaper batteries simply became the best economic choice for soaking up that midday solar surplus and shifting it.
And that must have knock-on effects elsewhere in the system.
Huge ones. Because batteries were suddenly so much cheaper for providing flexibility, the whole system re-optimized around them. Installed solar PV capacity, that single-axis tracking type, increased by 20% to basically charge these cheaper batteries.
More solar to feed the batteries.
Makes sense.
What about other generation?
Less needed for flexibility, so installed wind capacity and gas turbine capacity actually decreased in the model.
Okay, and the crucial link. What happened to the water storage side of things?
This is the kicker. The flexibility role that water storage could have played. It was almost completely wiped out. Water storage capacity plummeted by 93% in the 2030 model run.
93% drop. So cheaper batteries effectively kill the economic case for using water storage as grid flexibility.
That's exactly what the model indicates. The cheaper batteries just took over that role entirely because it was the lowest cost way to achieve it.
And looking out to 2050 in that cheaper battery scenario.
That scenario delivered the biggest overall cost saving. The LCOE dropped even further, down from the baseline $41.5 to $40.4 per megawatt hour. It might seem small, just a dollar difference.
But across an entire nation's electricity system, that adds up to massive savings.
Precisely. It confirms that, from a purely cost perspective, batteries paired with solar PV offer the most economical path to flexibility in this Saudi context.
Okay, let's synthesize this. The big takeaway seems to be, even in a country facing enormous water challenges where using water for storage seems intuitive, the actual least cost path relies on technology cost curves, specifically solar PV and batteries.
That's the core insight, I think. Water storage, while technically feasible, is hampered by the very high cost of the SWRO plants needed alongside it. Those plants demand baseload operation for their own economics, making them poor competitors against batteries, which are becoming rapidly cheaper and are inherently flexible. And there's another layer, too. The study suggests the maximum cost efficiency happens when battery cost drops are matched by similar cost drops in solar PV. They really are a pair. Cheaper storage needs cheaper energy to store.
That makes perfect sense. So the final thought for you, perhaps counterintuitively, is that the future of grid flexibility in Saudi Arabia might look less like massive water infrastructure projects and more like, well, continued cost reductions in solar panels and battery packs.
It points that way.
Right.
And one final nuance for you to consider, something mentioned in the study's appendix. This model focuses mainly on the plant costs. When you think about water storage flexibility, you also have to factor in the costs of potentially huge networks of pipes, pumps, land use for reservoirs. All that infrastructure adds up.
Right, the transportation of water isn't free. That likely further stacks the deck, as you said earlier, against water as the primary energy storage solution, even if it's essential for life.
It's certainly another cost factor to weigh in the real world.
A fascinating deep dive. We've explored the core findings of the role that battery and water storage play in Saudi Arabia's transition to an integrated 100% renewable energy power system. Thanks for listening.